So hello everyone, my name is Maria Mylova, and I'm currently a postdoc at the University of Tokyo in Japan. I'm also a visiting fellow, I'm another fellow at Perimeter Institute, and I'm currently actually going to be spending the next 3 months at Perimeter Institute. So if you're around, please say hi or send me an email. So I'm going to introduce open quantum systems and their applications to cosmology in this plenary talk. I would like to say that I'm new to this whole thing of recording your own video, so please bear with me. So let's get started. It is very important currently to understand the role of dissipative dynamics, especially as quantum technologies have been approaching regimes in which these kind of effects can become tractable. And indeed, even for us in high energy physics, we currently are having large amounts of data coming in and many future plan experiments, including in cosmology. And it could be that this type of open quantum system effects, such as noise and dissipation, etc., could already be in our data, or we could be seeing it in the near future. So I will first introduce what are open quantum systems. So usually we think along the lines of some system, which is a subsystem essentially, it's very small, interacting with a much larger reservoir or environment, and that could be, for example, a bath. And we can describe the Hamiltonian in terms of the two sectors, okay, the system and the environment, free Hamiltonians, and there can be a small interaction term between them. Now, in order for us, which we can only have access to just part of the system, of this total system anyways, with our experiments or with our measurements, to discuss what kind of dynamics or observational signatures are there, we need to find some kind of scale separation between the system and environment. And that is not necessarily the typical Wilsonian energy scale. It could be a horizon or something completely different. And then we need some averaging scheme so that we can integrate out the environment. So what we are left with is some kind of a non-Hamiltonian evolution together with the usual Hamiltonian evolution, which we can study to effects of dissipation, noise, etc. Okay. So let us start by introducing some of the most popular phenomenological tools. This will be the Limland master equation. And this can be used to model, for example, an atom or a qubit or some oscillator modes, which are weakly coupled to a large bath with a short memory. So here, you want to start with the von Neumann equation, okay, because this is like a Schrödinger equation. But with the Schrödinger equation, you can only study pure states. Now you can also discuss mixed states. And we assume some total Hamiltonian, which has a small interaction term. And from this, we can derive a master equation of the reduced density matrix. So we trace out the environment, okay, this large reservoir, and what we are left is a standard Hamiltonian evolution, but also some non-Hamiltonian evolution, which is given in terms of these so-called jump operators. And then you can depending on which of these type of models you want to discuss, you can decide some answers and try to solve this. And as you will see later, master equations are very useful because you can study a lot of quantum observables as well. You can use them to study all kinds of open quantum system observables as well. So they are extremely important. Now, in deriving this, there are some assumptions, okay? The Born approximation, where you assume that there is initially no interaction between the system and the environment. So the system is pretty much tiny compared to the environment. And then the Markovian approximation, where you assume that there is a correlation length, which is inverse the temperature, and this ensures that there is no memory effects, so that your results are essentially local. Now, for a long time, the Limland equation was used to study Brownian motion of a particle. But later on, Candero and Leggett, they wanted to study dissipative dynamics of a harmonic oscillator interacting with some bosonic degree of freedom, and by taking a path integral approach. Okay, so here we assume again weak coupling between the bath and the system. And of course, there is also an ohmic bath assumption, so that we can correctly match to the Langevin equation, which can be used to essentially describe the type of resistivity we need, like viscosity, for obtaining the dynamics of a classical Brownian particle at low frequencies. And as you can see, they derived a master equation that in this case describes some diffusion term and some dissipation term, and of course the usual Hamiltonian evolution. Now, in cosmology, we know that pretty much our systems are inherently out of equilibrium, okay? The universe is expanding, there is curvature, there is particle creation, quantum gravity, horizons, field interactions, you name it, okay? So one of the very typical examples where we use open, well, in the in-informalism, instead of, for example, the in-out formalism, is to study non-Gaussianity. So when we study correlations between 3 or more points in the sky, and this is because, so in the in-out formalism, there is inbuilt an adiabatic assumption that the vacuum state does not change. But in cosmology, we know that the Hamiltonian is essentially time-dependent, and there's particle production. It's almost impossible to decide which is the vacuum state. There is some arbitrariness there. And indeed, the in-formalism or Fugger-Keldy's formalism can get around this, as you will also see later. And it also allows us, on top of that, we can use it essentially to study dissipation and noise if we want it, okay? So that is a bonus. Another topic in which, again, there is out of equilibrium or open quantum dynamics involved are the initial conditions of inflation. So we usually consider a pure state. So we start in Burns-Davis adiabatic state, or we could assume there is some excited state, which we can obtain by a Bogolubov transformation. But some people have also looked into thermal states, for example, warm inflation. in which we assume that the inflaton is coupled to a radiation bath in such a way that it continuously dissipates part of its energy into radiation. And of course, that will lead into a mixed state from which then you can continue with standard inflation, for example, or you can choose something else. It could be some other type of mixed state that could have taken part very early in the universe. A lot of people are also studying decoherence and classicalization, and actually whether we're going to see mixed or pure states may depend on this, because in the end of the day, after a long period of expansion, we expect that the curvature perturbation is going to become essentially classical. But many people are asking the question, is there some way that we could see quantumness in our CMB observables? And we may be able to. And that's pretty much an open question at the moment. Now, another topic where, again, we study things like dissipative dynamics is, of course, the period of reheating, decoupling. For example, during decoupling, we have that certain species made departure from thermal equilibrium. And this happens when the interaction rate of these particles is much smaller than the Hubble rate. And to study this type of situation, we use the Boltzmann equation, which essentially describes how the energy and essentially the particle number is exchanged between different particle species via collisions or decay. So for example, you can use this to study energy transfer. For example, you can have a friction term which shows you that inflaton energy is drained into other fields during reheating, etc. So we usually write some Liouville operator with some collision operator which describes all these dissipative dynamics, which can be also rewritten in terms of the number density. Another topic where it's pretty much very important to use tools from open quantum systems is stochastic inflation. Now, in this case, the story has to do again with the fact that we are dealing with an expanding space-time. So in the city space-time, super-horizon modes essentially can be described by a first-order differential equation, classical equation, with a source term. Okay, this is some stochastic term, which is there because essentially all modes are going to experience, especially shorter modes, are going to experience this so-called secular growth. This means that even the UV modes that are very, very happily and healthy living in some ultraviolet regime eventually are going to be redshifted and enter some non-perturbative situation. So to deal with all of this, people coarse-grain the long-wave modes of the inflaton to derive a Langevin equation. This is what Starobinsky did few decades ago, which describes this stochasticity by some white noise. Or, for example, you can also express in terms of like a Fokker-Planck equation and study the probability density. So one of the most important topics that I think happened the last 2 decades on also an open quantum systems application to cosmology is stochastic gravity. And specifically, people derive the semi-classical Einstein-Langevin equation. So if you haven't seen it before, the idea here is that this is essentially the linearized semi-classical Einstein equation. As you can see, you have the typical regularized expectation value of the stress tensor, and of course you have some Baire couplings. You have to introduce counter terms, and the Einstein tensor, and as well a cosmological constant. But you can add to this a Gaussian stochastic tensor. And what this is trying to describe is essentially fluctuations of the energy momentum tensor to the semi-classical background. So this equation has been, of course, produced axiomatically, but also derived using functional methods by Hu and others. And it was also, it's very easy to see that this is gauge-invariant under noise transformations. I will explain later what this is. Again, we will go to the symmetries in open quantum systems very soon. So now this equation describes the situation where you assume that your system and environment are described by some quantum theory of gravity, and then of course, you don't have access to quantum gravity, so you're gonna integrate out all these high momentum gravitational fluctuations to get essentially some kind of an effective semi-classical description, which of course is going to contain dissipation and noise. So this is important for studying, for example, cosmological back reaction or back reaction in black hole scenarios, etc. But of course, that was all done 20 years ago. Nowadays, we need to update our tools and refine our tools and even extend them so that we can apply them to things like gravitational waves, which did not exist back then, or other phenomenological applications, as we have a lot of data coming in that we were not privy to 2 decades ago, okay? And of course, one will ask, well, great, is there a master equation for gauge theories? Well, the answer is not exactly. Of course, if we had a master equation, we could study pretty much everything from quantum information observables, such as entanglement and decoherence, or purity in the case of gravity. That is much easier to compute. Of course, we can study damping, noise, and all other kind of phenomena. But we don't have one. We know that in certain cases, people can derive gauge-invariant master equations. For example, Yukinao Akamatsu, he derived some Leblanc type of equation for describing a single quark in some high temperature setting. For example, that could be QCD plasma, by carefully integrating out all the hard gluons while preserving the color singlet dynamics. But of course, that is not widely applicable to all gauge theories, okay? So every time you consider some different system, you may have to derive a new Leblanc equation, and then you have to be very careful ensuring gauge invariance in every step. Well, what about Lorentz invariance? Well, Diossi showed recently that it is actually not trivial to try and derive a relativistic Lindblad equation. It's called GKLS, as well. The situation here is that whatever type of dissipator you choose for your relativistic quantum field theory, you're either going to break boost invariance, or you're going to introduce some acausal field equations, or some tachyonic instability, and so on. And so if you really wanted to have a genuine relativistic theory, is very likely, a Lorentz-invariant theory at least, sorry, is very likely that it will have to be non-Markovian. So you will expect to have memory effects, and that kind of makes sense. So together with collaborators, we started looking at studying open effective field theories with gauge theories in mind. So, I mean, the next question naturally you want to ask is, okay, forget about the master equation. Can I write some kind of model-independent parametrization for the influence functional? Which I will explain soon what it is also. So now, if you were writing just the standard Wilsonian effective field theory for closed system, well, we know the rules from Weinberg and many others. We just need to know the symmetry content of the fundamental theory, the particle content, of course. We expect the low energy dynamics. They're going to have there's going to be energy conservation. There's not going to be some energy transfer at least, or something like that. And there's going to be new physics. And we know how to parametrize them. Now, in the case of an open effective system, we need to double the fields, double the symmetries. We are dealing with non-local operators. There is going to be energy transfer, and we don't have a clear idea how to parametrize the new physics. So we could try to use some kind of bottom-up intuition, and indeed we recently had some people that a group from Cambridge that wrote an open effective field theory for electromagnetism in a medium. But they assume that there is a disformed off-diagonal symmetry in the setup. Or a different group from University of Tokyo, they wrote an open effective field theory for gravitational dissipative systems, and there they break the off-diagonal symmetry altogether. Of course, these two approaches are complementary, actually are one and the same, but either way, it will be nice to be a bit more clear about what is the right bottom-up intuition, and then how we can extend it so that we can enrich our phenomenology. So with my collaborators, we decided to take a more sort of systematic approach. So we go from top down. We are studying one of the most simpler sort of type of gauge theories, which is scalar QED. And we want to derive the influence functional. So I have been talking a lot about master equations so far, but now I'm going to finally explain what an influence functional is in the following talk. Okay, so that's why I haven't mentioned it yet, because I wanted to introduce you on the master equations. Now you can see the other side, how we do things top down. So we usually start with the density matrix. So that describes the full Hamiltonian evolution, okay, of the system. So we can, of course, evolve it forward with unitary operators as normal. And we can write the probability amplitude this way, okay, by simply inserting the resolution of the identity, and use also the path integral identity. And we can already see that we will need two path integral identities per field. So in this case, phi will be the electron in scalar QED, and A will be the photon, okay? And I have written the full density matrix in a field eigenbasis. So from this, we can, of course, extract, for example, the diagonal components will give you the probability distributions and amplitudes and correlations and things like that. While the off-diagonal components, you can use them to study decoherence, etc. And of course, this is subject to essentially the trace unity, bin Hermitian, and of course, positivity. Now, in the Swigger-Keldy's formalism, we can, as I said, we will have to double the fields because this is what was prescribed in the previous page by the probability amplitude. So we're going to evolve the energy, so the density matrix. We expect to have to double the field. So we have a forward and a backward branch in the closed time path contour. Which is in the forward contour, we have the class fields, which these are evolved by the unitary operator U, and then in the backward contour, we have the minus fields. And of course, this is subject to some boundary conditions at the initial and final times. And so this is how it looks once we put it into a path integral form. Okay, so we're summing over all the initial conditions, and we have doubled their fields, and of course our action. So we have the action in the forward and the backward contour. Okay, and of course here we can insert our favorite theory and now do some physics. Okay, for us this is scalar QED. So we are going to write down, for example, the free action, which is usually for the photon, and then there's going to be some interaction between the photon and the electron here, as well as a mass term for the electron. And then we're going to gauge fix and introduce the ghost fields. And if we rotate basis, it's a lot more intuitive to work in the sum and difference basis. So so the sum of the two fields will give you what we call it the classical field, or essentially referring to unitary evolution or whatever you want to think like. While the noise field, as we call it, describes the difference essentially between the two the evolution, the two branches of the contour, because you might have inserted some interactions, some operators, and now once you reduce your density matrix, you're gonna get this non-Hamiltonian evolution, as I'm gonna show you soon. So there's gonna be, of course, noise terms introduced into your action. So let's see how the free action first, so just the free photon propagator, and then interactions with the electron plus the gauge fixing terms look like in this kind of language, okay? And now we can show that these are, this action is of course invariant under the what so-called retarded transformation, but also advanced transformations. So these are the off-diagonal type of transformations. So essentially you double your fields, you double your symmetries, and you know that your theory originally is invariant under all these transformations. So now you're like, okay, now my full system, it consists of essentially the subsystem, which is the photon, and then the environment, which is the electron. I'm going to integrate it out to derive the so-called Feynman-Vernon influence functional. So what I'm going to do is I'm going to take the partial trace of this density matrix to produce a reduced density matrix in terms only of the photon. So I'm going to integrate out the electron. And in doing so, you can perturbatively show that there's going to be some interaction between the two branches of the closed time path formalism, which leads to non-Hamiltonian evolution. So essentially what leads to things like dissipation and noise is the fact that you reduce or you integrate out your environment, okay? This is what introduces this kind of non-Hamiltonian evolution. And if we put it into a more useful form, what is happening here, we will see that we will gonna get our usual corrections to the self-energy of the photon. So that will be unitary kernel, as well as some corrections coming from the fact that there may be noise and dissipation because we have integrated out the environment. So of course, these are gonna be sandwiched between the plus and the minus fields. And these are, of course, these kernels are, of course, highly non-local, as one will expect. So something that happens here may be affecting something that happens later on or somewhere else. So this is the situation you're dealing with. And we can see that the corrections to the photon self-energy are essentially just the typical Feynman propagators. And we have some momentum running in our bubble diagrams. As well, we also have the noise kernel, which is now in terms of bubble diagrams also, but these are written in terms of Weizmann functions. And we can immediately now substitute for the momentum representation of the propagators, normalize, regularize, the usual things, at least for the zero temperature theory. And so that these kernels, of course, satisfy the word identity, okay? So gauge-invariance is preserved when we reduce the density matrix. Now, regarding locality, let us look at something simpler, which is, again, the Kandera-Leggett model. So, as I said, it can be used to study some oscillator coupled to a thermal bath. And this can be described by two scalar fields. For example, we can integrate the sigma field out, and then we will get an influence functional very similar to the one I just showed you. And if we want to make it local, we can essentially assume that the initial state was thermal. So now we're going to have an extra bit added to our loop corrections, which is going to be make our loops thermal. So there's going to be a Boltzmann factor. Now we can see that if we are to very naively take the Wilsonian limit, so we say that the electron is very, very heavy, this is going to kill immediately both the thermal loops as well as the Weizmann functions, and you will end up with just a closed system, just the unitary dynamics. So we see from this that a closed system, a Wilsonian effective field theory is just but a special case of an open effective field theory. And of course, the Wilsonian limit is not a good limit for discussing open effective systems. In this particular case, if you want to study the high, for example, the high temperature limit, then you can, you will have to, first of all, break, in the gauge theory at least that I was just describing, break, of course, boost invariance. So you have to introduce some kind of frame vector. And you can then again write your kernels in a gauge invariant and Lorentz-covariant form by using these frame vectors. And now all the non-locality is inside these two functions that are going to parameterize essentially your kernels, your physics. And of course, these are highly non-local. They can be non-analytic. All kinds of things could be happening. But of course, if we were to assume again the Wilsonian limit, we will find that, for example, the unitary terms are going to drop out, and we expect this. We expect to get something like Euler-Heisenberg order E squared. There shouldn't be any contribution. As well, of course, all the noise terms and dissipative terms are going to drop out. On the other hand, if we take the high temperature limit, we may be able to recover a local theory, but this is something we are still looking at. So I don't have, I cannot tell you anything yet. You will have to read our paper, which we hope it will be out this summer. So now suppose that you want to now take what you have learned from this theory, from this derivation that we have done, and to use it as intuition to start building bottom-up descriptions for open effective field theories, for gauge theories. So now, assuming analyticity, and making essentially the assumption that was done in this paper here is a very good paper. You can try to read it. So assuming that these horrible non-local integrals are analytic, okay, then in that regime, what I'm describing is really dielectric, dielectrics, and I can then write a Lorentz-covariant theory in terms of the constitutive tensor, which is sandwiched between two electromagnetic field stress tensors. So this is obviously gauge-invariant. Immediately, you can see that. And of course, I can use this to immediately parameterize, for example, linear response theory, etc., as you will expect, doing sort of in this analytic limit of open electromagnetism. But of course, we think that we can get even something more general, which we hope it will be on our paper, so which will be out, as I said, soon. Now, moving forward, we would like to next study the symmetry breaking case, and then this is much more applicable to cosmology, where we know that time translations are broken pretty much during inflation, the universe expanding, etc., etc. And then use this, what we learn about attempting to do things from the top down to try and construct open effective field theories applicable to cosmology, and then do some phenomenology that could be to apply to linearized gravity or other setups. We could also revisit quantum gravity phenomenology. A lot has been done, and we have learned a lot about quantum gravity in the last 20 years. And I think there's a lot we could also be doing from cosmology side of things. And I think the most exciting thing is that these non-Hamiltonian effects can have observational ramifications that we can look for them in the data. But first, we have to be sure that we understand how to extend our tools, how to, for example, study, if we want to study things like cosmological correlators or interactions of linearized gravitational waves with various media, or whatever it is that we want to parameterize, we have to make sure that we understand the rules, and we have control over our effective field theories and the regimes that we can truly learn something about open quantum systems in cosmology. So this is all from me. Thank you very much for watching my talk. See you at the discussion session. Bye.